right, welcome everyone to my webinar today on how to predict and fix warping issues in your plastic parts. Okay, so um, for today's webinar, um, essentially what I'm going to do is I'm going to talk a little bit about how to predict warping issues in your injection molded plastic parts. Now, that's the easy part, right? So once you have predicted the warping issues, how do you fix it? So this webinar will show you some tools built into SolidWorks that allows you to create uh, anti-warp models that you can then turn into SolidWorks models. So that's really what we're going to look at today. So before we actually talk about warping, let's talk about shrinkage first. So what is shrinkage? Shrinkage is essentially this phenomenon when you create your plastic part in injection molding, and after you have filled the cavity, you've packed it, you've hold it, and before you start cooling the part, or even while you're cooling it, it it starts to shrink due to the cooling rate of the polymer. And there are many different reasons why your part can shrink, such as low injection pressure, short pack hold time or cooling time, high melt temperature, high mold temperature, or low holding pressure. So this graph, I really like this graph a lot. It really shows you what can affect or what can cause higher shrinkage in your part due to certain variables that you can actually control. So melt temperature, mold temperature, injection rate, part thickness, holding time, holding pressure. Now, shrinkage itself is not a bad thing. Typically, it's something that you really can't avoid. Your part is going to shrink, maybe by 1%, 2%, maybe even 10%, and you always compensate for that in your cavity. So you build it, 5% bigger to compensate for that shrinkage. Now, the question is, what does shrinkage have to do with warping? Well, warping itself is a distortion of the surfaces that does not follow the intended shape of the design. So you cut steel, cut your metal, basically your mold, to create a plastic part that has typically a linear shape. So it's either a cylindrical surface or has straight lines, and your part starts to warp as it's ejected from that injection molding or from the cavity. Basically, part warpage results in the molded in residual stresses, which is actually caused by the differential in shrinkage. So again, going back to about shrinkage, shrinkage is not a bad thing. It's only bad when you have different shrinkage throughout your part, which then can cause warpage. So if shrinkage throughout the part is uniform, the molding will not deform, it simply becomes smaller. So a lot of times, again, as I mentioned, you cannot really get away from a situation where your part is shrinking or even warping. So you need to be able to predict some of these defects early on to compensate it into your cavity. So you can build your cavity to so that it has that anti-warp. So when it warps, it actually warps into the shape that you want. Or if it shrinks into the size that you intended. So you're really cheating the system, right? So you're creating it so that it's still going to warp, but it's going to warp into the shape that you want. So to be able to do this, you need to know what the warping is. Well, one way, or the old way that this is being done in the past, is that you would build your part to size. With your you would cut your steel, and you would mold your injection mold your part. It comes out. You take your calipers, you measure how much is what the shrinkage is and what the warping is, and then you rework your mold, and you do that over and over and over again until you have the right part. So whether it's 2 or 3 times or 5 times or 10 times, you would have to do it over and over again every single time until you have the right shape and size. Now the hard part to that is when you change or you compensate for shrinkage, it can actually change the warp, that how the warp or how the part distorts. So it's not as simple as saying, oh, all right, so if my part is warping in the x direction by zero point 0.1 inch, I'm just going to add 0.1 inch, and it's shrinking by 10%, and I'm going to make the part 10% bigger. It's not just going to solve the problem like that, because once you compensate for that shrinkage, it's going to warp differently, and you're going to get different numbers. So really, it's trial and error at that point. You just have to keep reworking it till you find that sweet spot. Now, on the flip side is now you can do all this virtually. So basically, you can rework your mold for free, right? You can rework it multiple times, as many times as you want, until you find that sweet spot, and then you actually have a better place to start with, not the actual size, but you're actually maybe a few reworks closer to the final model. So going back to the old ways, if you're reworking your mold 10 times, now maybe you're only reworking it 3 times. So you save on those 7 times that you can actually do it virtually. So for today's example, we're going to take a look at this plastic part. It is a casing. I really like this part. I've used it multiple times now in many of my webinars like this. The reason is because it has a lot of plastic features that you're going to find in plastic parts. It has the ribs, it has the thin walls, it has multiple thicknesses, it has the clips on the side. So it encompasses a lot of features that you might run into when you're building plastic parts. The goal for this analysis is that I want to find what the shrinkage is, I want to see what the warping is, and then perhaps even see the in-mold residual stress, which is what is really causing the warp in my part. So let's jump to SolidWorks. Take a look at this. So this is my part in question that I mentioned. This is a plastic part. Just checking to see if there's any questions. All right, and for this analysis, obviously, I'm going to use SolidWorks Plastics. You can see that I've already turned it on under my SolidWorks add-in right here, SolidWorks Plastics. And I actually have a few studies already run. And what I'm gonna do is I'm gonna start by showing you my fill pack warp analysis that I did. And so this webinar, I'm not really going to jump into every step that went into creating the plastic part itself. I really wanted to focus on the warping side of things. So what I'll do is I'll quickly go over some of the variables that went into creating this plastic part, and then we'll talk about warping, and we'll talk about how we can fix that. Okay, so for the first configuration, you can see that I have 2 studies here. This is my fill pack warp study, and then I have another study which is called fill pack warp study. So we'll talk about this first. So this is a faster way to execute your warping, and what essentially does is it goes through your fill analysis. Basically, it fills the cavity, and then it runs the pack analysis. So basically what happens during the pack and hold stage of your injection molding process, and then it will basically fast forward to your warp analysis. So it really doesn't run a cooling analysis. It makes an assumption that the mold has a constant temperature, which is not really the case, because when you have cooling lines, your mold is not going to be constant temperature. It's going to be a change in temperature, which is what the other analysis is. I'll show you that in a second. So you'll see that my results for this first set is it runs the analysis a lot faster, but the results are a little bit more conservative. So you have the option to say, all right, well, if I want to run a quick analysis, I want to see what's going on, you're in a black box, you don't even know what's going on. You can run this just to get an idea, and then when you have more time to dedicate towards the analysis, then you can run a fill pack warp analysis. All right, so for this analysis, I've just used a very basic ABS generic material, and for my fill settings, I've set the filling time to 0.8, melt temperature to 230 Celsius, mold temperature to 50, and injection pressure limit to 100. So as I mentioned, that a lot of this, at this point, even after your fill analysis, you can actually get quite a bit of results that typically you can't get in real world unless you've actually run the entire injection molding cycle, right? So because what it does is you're able to plug in numbers as placeholders, and it makes a conservative assumption. So it makes constant temperature, and it will give you some shrinkage information even early on, even in your filling analysis. So if you look at under advanced, we even have the ability to set a gravity direction. Now gravity direction is very important when you're talking about warping. So in your warp analysis, it also will ask what a gravity direction is. Essentially, once your part has filled in your injection molding machine, what direction does it fall out of the injection molding machine? So that's the gravity direction. So in this case, the part is being filled, I believe, in one of the corners, and then it falls in this direction. It falls out in this direction. So it falls out in the Z plus Z direction. So it falls down here, falls out. So that is the gravity direction. Okay. So again, even in your fill settings, you can put in quite a bit of information, and as part of the fill settings, you're able to get flow results. And even within that first step, you can already predict volumetric shrinkage. But just keep in mind, again, this is just conservative results, quick analysis. If you want to just get an idea of what's going on in your part, you can just run this quickly and get some of that idea. For our pack settings, I've set the pressure holding time to 5 seconds, and pure cooling time 18 seconds. Again, here's another assumption that we are plugging in. Rather than actually running cool analysis, we're just saying our cool time is going to be 18 seconds, and allow the software to make calculations and tell me what's going on in the warp, how the part is going to warp at the end. So under your pack settings, you also have more results. So if we read pack, now you have a little bit more better results for volumetric shrinkage. I mean, if you remember, recall for the fill settings, it was a little bit on the higher side of 9%. So once we've already run the pack analysis, this number drops a little bit. So this is actually more, it's closer to the real value. Even at this point, we will have some residual stress at post-filling end that you can start to predict some of the warp that may happen in your part. Okay, so fast forward to warp analysis itself. For our warp setting, all we did was ambient temperature. So what is the temperature, room temperature? 30 Celsius. Yeah, that's about right. In injection molding house, typically you have a lot of machines running, so it's not going to be 20, 25, 26, 27, which is typically what most room is in. It's going to be a little bit higher. So 30 it's a good number, and of course the gravity direction, what direction that the part falls out. So now that I've set my warp analysis settings, you can actually take a look at our warp results. So I'm going to say all effects displacement, and we can take a look at how it's displacing totally. And you can't really see it much. I mean, you probably won't be able to see 0.89 millimeters, but what this software will allow you to do is increase that deform scale, so you can actually see in which direction that it's deforming. So if I increase this by 10 times, you can see now clearly how it's deforming. So that 0.8 is probably affecting this red area. So this is where it's warping the most. Also, you can see that there's clearly quite a bit of warping going on here as well, and definitely quite a bit of shrinkage as well. So shrinkage was about 9%. So besides being able to see a total deformation, you also be able to see your warping in the X direction. So in this case, probably a Y direction would be better. So this is in reference to Y. So you'll be able to see how it's warping. It's going from 0.5 to 0.7. You'll be able to break down the displacement. So whether it's the in-mole residual stresses that's causing the displacement, or the quenching thermal stress, what is causing the more displacement in your part. Addition to displacement, you'll also be able to see your sink mark profiles. And just to reiterate, you would be able to get sink mark results even in your flow analysis. However, your warp analysis will give you more precise sink mark results. So, so that's really a quick overview of how you would set up this analysis and get to your warping analysis. But for this example, I wanted to get my real warp part based on cooling. So it's not just constant mold temperature. The mold temperature is changing due to the cooling lines. So we're going to add that on. So I'm going to pick now my fill pack warp analysis. And that is the sequence in which this analysis is being solved. And you can see that I have these lines here that are sketched in, and these lines are essentially the cooling lines. So it's actually very simple to set up cooling lines in SolidWorks Plastics. You just sketch it in. You see that it's all just sketch lines. And if you come into your boundary conditions, you have your cool pipe. All you need to do is just select those lines, and you'll be able to create the pipe. So I have 4 pipes. You can see that I have 4 individual lines. You'll be able to select the coolant material. So in this case, whether it's ethanol or oil or water or some form of coolant, coolant 25 or coolant 45, you can pick whatever it is. So in this case, it's just water. It's going to be room temperature at 30 Celsius, and you can also, of course, pick your flow rate as how it goes in, cold in, and hot coming up. Okay, so if you want to reverse the flow, you can as well. All right, so that is our cooling lines. So now we probably would get much better results for our warp. So we'll go right to our warp results. And we can see our total stress displacement here, 0.9973. And in addition to that, I also want to look at my shrinkage. So this is shrinkage with cooling lines, with the cool analysis pre-ran. You can see that it's a little bit different. Before it was about 9.1, so this is 9.2. So previously it did a pretty good job predicting the shrinkage, and obviously now it's a little bit better. So 2 things that I want to keep in mind as I try to fix this warping issue, right? So I'm using the software to predict the warping and shrinkage, and now I'm going to use SolidWorks tools to try to fix this warping issue. All right, so this is 9.2. Actually, if we look at the part itself, it's probably more on the lower end. So I would say it's probably about 1% in total. If you look at the total part itself, there's maybe one or two areas that it's on the higher side, which I wouldn't be too worried about right now. All right, and if you look at the warp, let us deform this a little bit higher just so that we get a better idea. All right, so just taking some mental images here, because I am going to physically try to distort this part to match the anti-warp of this. Okay, all right, so have a pretty good idea of how this is warping and shrinking. Okay, so now that we have our warped part, SolidWorks has this tool under results which allows you to export. Okay, so if I right click export, select that, it gives me a few options. I can either save this part as a surface solid for some analysis softwares. You can also do it right. You can also plug it right into SolidWorks simulation, where it takes the in-mold residual stresses and runs a nonlinear analysis for you to see how it's affecting your part, your plastic part, and you'll be able to transfer the material directly from SolidWorks plastic. So I'll probably keep that for a webinar another day. So stay tuned for that. But for this webinar, what we're going to do is we're going to actually create an STL model. So I'm going to say model STL, and for the deformation factor here, 1 is the deformed part. Essentially what I'm looking for is the anti-warped part. So what that means is it warping in the opposite direction, because that is the shape of what my cavity has to be. So essentially I'm going to warp it in the opposite direction, and then when I run the analysis and it warps back, it will warp to the original shape that I require, the intended shape. So what I'll do here is I'll actually drop this down to -1. So 0 is your actual geometry, the geometry that you created. 1 is the deformed part due to shrinkage and warping. And -1 is the anti-warp, anti-shrinkage. And I'm just going to hit export here, and this will allow me to save this part as an STL. Okay, you can see that I actually already saved it, so I'm not going to resave it again. But all you need to do is just hit save here and you'll be all set. Alright, so here's the fun part. Let's go ahead and open up that anti-warped part. Come in here, say STL. I'm going to make sure it's in the right unit, so it's millimeters. And I'm just going to bring in a graphic body. I don't need a solid body, a surface body. So this is going to be quick and easy to bring in. Open. All right, and that is my anti-warp STL graphic only part. So it's not, you can't click on it, you can't really do much with it. What you could do with it is you can use it as a template to basically turn your SolidWorks part into this part. So what I'll do here is now I'm going to say insert part. I'm going to look for my SolidWorks part, my top casing. I'm just going to make sure that I have the right units here. All right, millimeters. Insert part. Open. And SolidWorks actually allows you to snap right to that part. You can see how it's snapping to it right away. And if I click, you can see that it is superpositioned, and you can see the warp part versus the actual geometry, anti-warp part versus the actual geometry. So to make life easier, what I'm going to do is I'm actually going to change the appearance of this to perhaps something green like this, and I'll also make it transparent. Okay. Oh, just want to turn the body to green. All right. So now what we can do here is now we can start to deform our plastic part to match the STL file that we have here. So actually what I'm going to do is I'm just going to remove the appearance because you can't really see it well. There we go. And it is only for the body. There it is. So now you can actually see it superimposed. The warped, the anti-warp part is the gray, and the geometry is green. Okay, so in SolidWorks we have some tools under features. So if you look under your insert features, we do have a tool here which first allows you to scale your part. So I would always start with just scaling your part up close to something that you had for your shrinkage percentage. So in this case I'm going to say scale. I'm going to pick that body, and what I'm going to do here is I'm going to say 1.01. So this is 1%. Uniform scaling, scale about the centroid. I say okay. Now you can see that the part is starting to match the gray area. To look at it closer, you can actually see it here. So what I'll do is so you can start to look at how my how I was able to scale that part up to start to have it start match my anti-warp part. So I think I can actually scale it up a little bit more. I know I said it was about 1%, so maybe I'll do closer to 2%. So maybe I'll do 1.7, and you can see that that is much closer now. Okay, so essentially what I'm doing here is I'm taking my geometry, my solid geometry, and I'm using SolidWorks tools such as scale to try to scale it up to the anti-warp model. So now that I've scaled it up, the next thing that I want to do is I want to compensate for that distortion, and for that we can use our flex tool here. And under our flex tool you have a few options where you can bend, twist, taper, or stretch your part. So sometimes you might see that your part is warping in one direction like that. In those cases you can actually use stretch. You can stretch your part out. So for this case I think the bending is going to be a good option. So I'm going to pick the part, and what I'll do here is I'm actually going to pull this out a little bit more so I have more control over my bend, and just slowly increase the angle here. So I don't know if you can see, but as I'm increasing the angle, there's less and less gray, which means my geometry is starting to match with that anti-warp part. So just be careful as you're distorting this part, as you're bending it up. It's also going to bend from the bottom. When it's moving geometry, it has to take geometry from somewhere else. So you can see that this geometry is moving up here. So one thing that you might do is probably bring this closer. Okay. All right. And just for finishing touches, I'm going to scale it up a little bit more to compensate for that removal of geometry at the bottom. So maybe I'll bump this up to 2. And you can see that I have a pretty close match to my anti-warp part. All right, so at this point you can actually come in here and you can either delete this body, or you can just simply hide it, and there you go. This is your anti-warp part, and this is the part that you can start with in creating your cavity in your mold. So just to recap here, what we really did was we took our SolidWorks part, just basically the actual geometry that you know for your final part, the actual geometry for your final part, and that's how it was created. You ran a SolidWorks plastics analysis on it, fill, pack, and warp analysis. You created or exported an anti-warp part. You used an STL model to superimpose it over this actual geometry, and then you used SolidWorks tools to bend or twist or scale the model up to match that anti-warp part. So now when you run that analysis again, it should shrink and warp into your desired shape. Now, if you choose not to use SolidWorks to create an anti-warp part, that STL file superimposed with the original file will still give you a really good idea of how your part is warping, and that can also help you streamline your plastic part design. So just to go over what we did here today, we used SolidWorks Plastic as a solution. It allowed us to obviously fill the part. We were able to use the analysis results to look at our shrinkage, give us an idea of how much to scale that model up. Initially, I said 1%. As I looked at the model, maybe it was closer to 2%. And also, we were able to use warping warping analysis to warp the part to predict the warp, and then create an anti-warp. And last but not least, we also considered the cooling process within the analysis to ensure that we're getting the most precise results when it comes to warping. So it's not just a constant mold temperature. The mold temperature is different at different areas due to the cooling process. Okay, so before I open up for questions, I just wanted to let you know that we are running an simulation open hours event, design validation event in every office, Rochester, 22nd, Syracuse 23rd, Albany 24th, and Buffalo 25th. It's a one-on-one session with the simulation specialist where you can come in, you can talk about anything that you saw today that you're interested with plastics, perhaps anything with simulation flow, which is our CFD package, and SolidWorks simulation, which is our structural FEA analysis. Again, sit one-on-one with the simulation specialist, talk a little bit more about your application and how we might be able to help you streamline and make that process better, being able to validate your parts better with some design validation tools. And of course, you'll also get a chance to play around with the software yourself. So you'll be able to fire up SolidWorks and use these softwares with the guidance of a simulation specialist. Thank you for joining me today, and I hope to see you all in my next webinar.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.